right. Okay, we're live. Hello, everybody. If you can hear us, please send a message, and don't forget to write your name in the chat so that I will check you in. Welcome to another session, Launch and Learn session. And today we will have Amir Hajiam from Script, and Amir is will tell you how to pronounce the correct name of his company a bit later. Amir is a okay. Sorry about that. So today we'll have Amir Hajiam give us an overview of mathematics of deep learning. Amir is a director of data science at Script. Amir formerly was an astrophysicist he was an astrophysicist by training and a data scientist by trade. Amir is he worked as a director of AI research at Thomson Reuters previously. Amir's job is to lead teams of data scientists and engineers to design and build end-to-end products powered by machine learning, statistics, graph analysis, and NLP. Before Thomson Reuters, Amir worked as a postdoctoral research at the University of Toronto, as well as Princeton University. So without further ado, Amir, I will give you the mic.
Thank you very much. And hello, everyone. We are going to talk about mathematics of deep learning. And in a few minutes, I will tell you what exactly we mean by that. And the plan for today is to walk you through some math that you most probably don't see when you start doing deep learning, and also do a deep dive into an interesting aspect of it. So before getting into the mathematics of it, let me tell you about us. So I'm the instructor, and I work at Script as the director of data science, as you heard. What is Script? Script is a business built around books, and we are a company of a bit more than 200 people. The company started in San Francisco, and now we have other offices in other locations, especially in Toronto. We have our data science team, and that we are building and growing. And what we do is that we make different realizations of the written word in different formats available to everyone in one single app. So you can think about Script as the Netflix for books, or Spotify for books, or and audiobooks, and everything generated in a format of some kind of written word. So that's about us. Now, what we want to do today is to talk about these aspects of mathematics of deep learning. So in about 10-15 minutes, I will walk you through the universality theorem, which says, which is about the underlying reason behind why deep learning actually works. And because when you start doing deep learning, you know, if you have done it, you know that it's pretty much brute force. You take some matrices, you multiply, and then you apply some nonlinearities to that, and you magically get some very interesting answers and results. And the question is, why does it even work, and why are we so hopeful about that? And then we talk about what kind of math we will be talking about in the next 3 sessions. What we will learn in this course, I'll show you an overview, and then we will talk about what you will build if when we start uh, doing a deep dive into the course. So the the main problem in machine learning is usually finding an approximation to a function. The function is the thing that maps the input space into an output space. This is a very abstract way of saying that I have, let's say, a set of images of cats and dogs, and I want to find the function that takes a cat, takes an image from me and says whether this is a dog, this is an image of a dog or an image of a cat. So when we talk about the function, we are talking about what happens there. We are talking about, let's call it a computing element there that takes the input and tells you and gives you the output in the domain that you're interested in. So you can look at it this way. A machine learning task could be a classification, like what we saw. It takes an image and says what is in the image. It can be applied to a natural language domain. It can read a text and it can pick words and classifies the words into the categories. Like it says Toronto, I say Toronto, I know that Toronto is a city. So this is another kind of classification. Or it could be a form of regression. I can give it a bunch of numbers on a plot and ask what is the value of this function where it is missing. So the goal is to approximate that thing in the middle, which we call it the function, to a high accuracy. And high accuracy um, is an accuracy that is good enough for us to do our job. And it really depends on the kind of job that we want to get done. Now, in the late 80s, there were a series of papers published about how we can solve that problem and what is the most promising way of doing that. And so you can go ahead and read these papers that I'm citing here. They are a bit complicated, and we are going to look at the proof, or I would say a demonstration of what is in those papers visually and in an interactive way, to show you, to give you a very good understanding of why deep learning actually works. And so the soul of these papers is that you can take any continuous function, um, let's say the functions that we talked about just now, take any of them as long as they are continuous. You can find a good approximation to those functions by a multi-layer feed-forward neural network with some hidden layers and some activation functions. Now, what are each of these in mathematical terms? We will see that more as we go through the course in the next session, I think. But here we will do a very intuitive walk through that. So, what this is saying is that, and we will see why. It's saying that we can approximate any function that we want with a with a neural network structure. All right. Now let's see how that works. So the function that we want to approximate could be as complicated as we want. We are saying the universality theorem says that take this, you can represent it by a structure like this, an architecture like this in neural networks, and then you have your solution. How does it work? So what I will be showing you here, I have taken from this great website of neural networks and deep learning. If you're not familiar with it, it's a really nice book here, and I highly recommend you to go and read this. It's as you will see, it's very helpful in understanding what we will be talking about. Okay, so what is the building block of everything that we are going to talk about? So let's look at an artificial neuron. An artificial neuron has some inputs. It takes some inputs, and which are, let's say, some numbers, x1, x2, x3. It multiplies the inputs by some weights, sums them up, and then applies a nonlinear function on top of that, and decides whether this neuron actually fires or not. Okay, so let's say I have x1, x2, x3 as my inputs, and to just to simulate it, this is a super oversimplified view of an actual neuron, but let's just assume that we can imagine this is a real neuron. And so you get three inputs. The three inputs are let's say the temperature of the room, the intensity of the sound around you, and the intensity of the light. Okay, and then your neuron takes all of these in and decides at what point you should start running when there is a danger. So if the temperature goes too high, or if there is a lot of noise around you, this neuron fires. So basically, you take these, you multiply by weights, you sum them up, and then you say, is the summation below a threshold or above? If it is below a threshold, you do nothing. If it is above the threshold, the neuron fires and it returns 1. All right. So this is the usual artificial neuron thing. We can put a few of these together and build a very simple neural network. In this case, my input here is shown by X. I have just one input in this image. And then I have the output, which is f of x, any function that I want. And then I have some hidden layers. Hidden layers are hidden because they are not visible. They are neither the input that we are getting from the environment nor the output, which is the function that we would like to get. All right. Now, as we saw in the previous slide, we take the input, we multiply it by a weight, and then here we are also adding a bias. We will talk about all of this later, and then we apply the nonlinear function on that activation function, and that tells us whether this neuron will fire or not. Okay, as we saw, this is basically the output of this gives me a step function. Depending on the input x and the weight, the neuron decides whether to fire or not. The function that I get only has one free parameter, and that is the ratio of the bias here divided by the weight. That's if I know the bias, if I know the weight, I know at what point this is going to cross the threshold. All right. So that is that is the output of the top neuron. Now I have the same thing for the bottom neuron, which means that I have, if I put them together, I have a step function coming up from the top part. I have a step function coming from the bottom part, and then I can add these two in a linear way. I can multiply this top result by a weight function, by a weight value. I can take the step function from the below, multiply it by another weight, and sum them up. So I will get the sum of two step functions. Now let's see what it means. I'm going back to the page that I showed you. So this is what I showed you. S is the ratio of the bias divided by the weight. I changed that, and you see that the shape of my step function changes like that. Now this is for the top part. I have one for the bottom node as well, and I put them together. I get two step functions like this, and you can see that if you change the parameters, you can control the shape of the sum of the two step functions together, right? So that's basically it. And then you can see that for some specific values, you can combine these the weights to get a top hat function, which is very interesting and useful, because with this you can basically approximate any function with enough of this. How do we do that? So this is basically what I showed you. You put the weights together, and you will see that there are basically three parameters here that you have, which are given by the ratios of the weights that we saw above, and you can control the width of this function and the height of the top hat function. All right, now we go. That's for two hidden neurons. Now, if I add more neurons, I can add more top hat functions. For example, if I increase the number of neurons to 4, I can fine tune the weights to get 2 top hat functions, and then I can control the height of these by changing the weights that I have. Okay, it can be positive, it can be negative, and I can change the distances and the widths of the 2 top hat functions. All right, so that's interesting. We doubled the number of hidden neurons here. We doubled the number of top hat functions that we can generate by a very simple neural network architecture. Now, where to go from here? We can keep adding more hidden neurons here, and then with the parameters that we have, we can control the weight and all the details of these top hat functions. All right, and now you can guess what's next. So let me go back to the slides. Now we want to use what we saw to approximate a function with n top hats, with a number of top hat functions. Let's assume we are looking at this function. This function is pretty complicated, as you can see. But then what we can do is we can add a large number of neurons here, hidden neurons here, and then we can break the x interval into n pieces, and fine tune the weights to approximate the function with these. Let's take a look at how it works. So here, this is our function, and this is our structure. So the first bit, I'm approximating these wiggles with this straight line going through the wiggles. The second one, let's say this is a good approximation. The third one, we will do this. The fourth one here, and that one. It's a success. So we got an approximation, a discrete approximation to our continuous function by a 10 node one single hidden layer neural network. So that's interesting. Is this a good approximation? No, this is terrible. This is like the 0th order approximation, but it has some information about, okay, so here my function is negative, is around -1, and then it goes close to 0, and then it goes positive when x gets close to 1. Now, can I do better? Yes, I can. To do better, I can add more hidden neurons here, which means I will break this into smaller pieces, and then I will be able to come up with better approximations for my function. But as you can see, this is just a matter of adding more and more hidden neurons to that. And if we build a large enough architecture, we can approximate any complicated function with that. Of course, this is not a proof. This is just a visual demonstration of what exactly this means and how it works. So does it mean that we can take any problem and throw it at a deep neural network structure blindly and get an accurate solution out of it? It doesn't necessarily mean that, because there are more complications there. First of all, this is an approximation. We need a lot of data to get good results, and sometimes for some problems the data that we need is huge and massive, and maybe it needs a huge time to compute and converge. But essentially what we are seeing here is that complicated problems can be solved if I build a large enough, sophisticated enough deep learning structure, and if I have enough data, and if my problem actually, my solution converges to a solution, to an actual solution. All right, now let's take the notation that we had. You remember I showed you this. We have some inputs, we have weights, we multiply weights by the inputs, sum them up, and then we apply an activation function on top of it to get the output. Can we simplify this? Actually, if I look at these, if I take the input, so the input and the weights have the same dimensions, right? So I can look at the input as a vector in this case, and then because I'm doing an element by element multiplication between the input vector and the weight vector, I can actually write it as a dot product between the two vectors. So this is the weight vector, this is the input vector, and this is the dot product of the two vectors. This is what we will be talking more about in the first session of the course. So we can replace that part with the with this, which shows that we are doing a dot product of the weights and the input. We are adding bias, and then we are applying an activation function on top of it. So if you look at it, this is all about multiplying some vectors and matrices, and then adding some matrices, and then finding the weights, as we saw in the previous part when we were approximating the function. And then to find the weights, we have to explore the parameter space. We have to find the set of weights that actually solve our problem. And that's it. So this is how we solve a deep learning problem. We start with a problem. We find the weights and the functions that give us the right approximation, the best approximation to the function that we are interested in. And to do that, we need to do a lot of matrix manipulation. We need to solve some optimization problems, and we need to take some derivatives. And these are the topics that we will be discussing in this course. What will we learn exactly? So before I start this, I would like to pause for a couple minutes and see if there are any questions so far before we get into the actual syllabus of the course.
Yes, that's right on time, because we do have a few questions.
Excellent.
I think a few people are a little confused about, can you go back to the previous slide?
This one?
Maybe the one before that, the one where there's a H. Yes, a lot of people are asking what is H exactly, and Owen is asking how to tune H in the deep learning implementation. Is it like one of the hyperparameters?
Yeah, so we will talk more about the parameters and the weights and what exactly they do. Here, H is a reparameterization of. So if you go back here, so you see that once we took W and B and we renamed the ratio of B over W, we renamed it as S, and because there's only one parameter here that matters, and that's the ratio here. And then we take the results of the two hidden neurons, and then we multiply them by two weights, W1 and W2, and H is a combination of W1 and W2. And again, so that's a that's a reparameterization of the problem. If you want to read more about it, it is, so if you go to the page that I showed you, and if we go up, the H is defined here. Yeah. So this is where we go from the weights to the H. And so as a result, this is a combination of all the parameters that we have in this to make sure that we have just one single parameter that gives us the height of the of the top hat.
Okay. Alice is asking what is the tool you're using? I think it's just the chapter 4.html page on the neural networks and deeplearning.com, right?
Yes. So this is chapter 4 of this book and web page / book. If you go to the first page, this is a free online book, neural networks and deep learning. So I'm using the interactive plots that we have on that page. They're as you see, they are pretty awesome to understand what's going on.
Yes, it looks great. Natine asks, what exactly is the function when deep learning algorithms are applied to identify a cat, for example?
Yeah, so that's actually an interesting question. A function, if you're asking what is the closed form of that function, we wish we knew that. It's a very complicated function that that relates every information that we have on every pixel of the image to one of the two classes of whether this is a cat or a dog. And this is, so usually when we talk about deep learning, we use deep learning in problems where they are so complicated that we cannot really come up with a closed form to represent the problem. If you're familiar with statistical inference and predictive analytics in the traditional form that we all learn in the school, we usually, what we do is that we have a process. We take the process and we represent it by a function. And that function is, we derive it from first principles based on our understanding of the process and what is happening, the physics of the process or the biology of the process. And we have parameters there and we solve it, and that's the solution. For a lot of problems that we deal with in day-to-day life, where we only are interested in the prediction, in the result of the prediction, and not the process itself, the function is so complicated that we can't not really write it analytically. So this function, look at it as a computational component that takes some input and as when I say input, I mean, let's say an image. and spits out two categories, whether it's a cat or a dog. So it's I can't write it as an analytical function if that's what you're asking.
Okay, cool. So just a quick time check. We have about it's 12:40, so we have about 20 minutes. We do have a question about the prior reading before the workshop, but I think we need to talk about the workshop first. So yeah, Amir, I'll let you continue.
Yes, sure. All right. So what we will be learning in the workshop. In the first session, we are going to talk about the foundations. And in the foundations, we will start by the computational linear algebra. What is it? How do we do multiplications and inversions and everything that we do with matrices, and what does it mean? What is a tensor? And then how do we apply it to deep learning, and what are all these terms that we keep hearing about: parameters and functions and weights and biases and nonlinearities and activation functions and loss functions. All right, so a, um, an overview and definition of all of these creatures that we usually deal with them in deep learning. And then we will do a hands-on session with PyTorch. We will pick PyTorch as our tool of preference. And we will see how we do each of these um, linear algebra computations, how we do them in PyTorch. How do we multiply tensors or add tensors or whatever we do. And and we look at the loss functions in PyTorch, and we will do some exercises. Ignore the exercises that I've written here. We will come up with some relevant exercise for different levels of the audience that we have. In the second session of the workshop, we will talk about the mathematics of information and what exactly we mean by that. I'm going to focus mostly on convolution. What is a convolution, and what are the applications of the convolution? Um, how do we compute convolution? What it means, and what can we do with it? All right. And if we have enough time, we will talk about other matrix manipulations like factorization and dimensionality reduction. If not, we will give you some pointers to good resources to go and read about and learn more about it. In the hands-on session, we will take an example of an image, and we will look at how we extract information from images using convolution. The idea is to see how convolution actually works in a real world situation, and we will use it to detect edges in images in PyTorch or in Python. And then in the final session, we will talk about the mathematics of finding the solution. That would be the optimization and taking derivatives, and how we converge, how we go from an initial architecture of randomized weights to a deep learning solution with weights that actually solve our problem, and what it means to do that, and what it takes to quickly solve that problem, and what are the tools that we have in PyTorch, and we will build an image classifier in PyTorch, a very simple application that helps us see how everything that we have learned so far in the workshop, they come together to build something useful. And then we will briefly talk about what is next. So now I know the mathematics of deep learning. I'm not scared of that anymore. It all makes sense. Now, what is my next step? Where should I go from here? And the hands-on session, the goal for the hands-on session is to help you see some of the things that you learn in every session of the workshop in action, you know, and and to um, relate the abstract ideas of linear algebra to things that you can actually do on images and on things that you can read in Python and do real stuff with it. It will be very simple because the goal of this course is not to solve complicated problems for you or to make you build something very sophisticated with deep learning in PyTorch. That is not the goal or focus of our workshop. We want to focus on the meaning of different mathematical creators here, see how they are used, and see some examples of using them in PyTorch. And what should you study beforehand to be ready? I think there are two useful resources that will help you. Basically, you don't really need to study much for this. We are starting from this is the beginner course, so you don't need a lot of background for this. Just make sure you remember Python, you know how to use Python very well, and it will be helpful if you read the Aon Goodfellows et al. Deep learning book. So it is called Deep Learning Book, and it is available for free online. If you go to the first chapter, the first chapter is what we will be dealing with. So applied math and machine learning basics. Read that part at home. It is from the part one of the book. And that's pretty much what you need for what we are doing. All right, so that's the overview. We are going to start in a couple weeks, and I'll stop here. We'll take more questions if there are more questions.
Yes, absolutely. We have a lot of questions queued up. Just before we go into the question, I want to mention that we do have a 30% off discount for a short period of time. So if you're interested in purchasing, please come message me or just message me about the about discount code. So let me scroll all the way up for the first question. Oh yes, the first question is about a prerequisite reading. Jiri asks, would you recommend reading the online book prior to the workshop, or would that be the best source to get prepared? I think he was referring to the deep learning book you showed earlier.
Yep, absolutely. Yes, it will be helpful. It's a very good book.
Okay. Owen asks, this is a question about your explanation earlier about using a neural network. What it means. What does function mean? So all this looks like supervised learning. Is it the same approach for unsupervised learning?
Yes, it's a bit different, but basically, let's say you have a you have a bunch of points and you want to find the outliers. So basically, you want to find the hypersurface that separates the two, and the function is the geometrical function that describes that hypersurface for you. So yes, it's basically similar in terms of if you think about the function that there is a function that you are learning, there is also an underlying function there that you need to learn.
Okay. In the context of Venkatesh asked, in the context of object detection, how does deep learning differ from image segmentation plus pixel tagging? Can't both approaches be used to identify a cat in an image?
Yeah, basically um, well, there are different ways of solving problems. I'm not familiar with the combination that you mentioned. It basically, if it solves your problem at the accuracy that you're interested in, that is your solution. And there are many different ways of doing that. Some solutions are optimal, some of them are not optimal. And the whole game is to find the solution that is optimal enough for you and solves the problem for you. So it's not there is not just one solution usually for a problem. And sometimes you can solve a problem with deep learning and then you can go back and say, actually I didn't need deep learning for this. I can use it, I can solve it using an SVM approach, or some other approach which is um, computationally less heavy and less expensive. And so finding the solution is the objective here. Whatever solves the problem, that is what we are after.
Okay. Then we have two, I guess, feature requests in software terms. And the first one is Alice asked, like, can you cover factor analysis as well? And she was specifically mentioning PCA would be too simple. Would be nice to cover advanced ones such as non-negative matrix
Yeah,
factorization.
and NMF. I'm sure you saw that at the bottom of the page that I was showing. We will see how much we can cover. We will either cover it or we will give it to you to do as an exercise at home. And it's so let's talk about the second feature request as well, and I'll tell you something about how we are going to do it.
Okay, the second feature request is the topic of explainability. That's basically Jorge is asking if this can be covered.
Um, Again, that we can give you some pointers to things to read and discuss, and then we can have sessions outside of this. But so explainability is not, it doesn't fall under mathematics of deep learning. So we are trying to keep the focus of the workshop very narrow to make sure that we will get there. Otherwise, there are so many different things to discuss that will be very difficult to actually do anything, or to finish in 3 sessions. And something to keep in mind is that unlike university courses where you are required to take an exam at the end of the course, there is no exam here. You're here because you're interested to learn more, and as a result, we are not going to do it in a school course way. So we will talk about stuff, we will discuss a bunch of stuff, but there are many things that I will I will mention and I will give you links and pointers and books and articles to read and things to run and codes to write and problems to solve, and the rest of it would be, so 90% of the whole workshop will be done by you at home after the session. The sessions will be designed to show you what is interesting and important and to enable you and give you enough information to go and figure out and discover for yourself. And so hopefully by the end of the third session, you will have learned fishing instead of having earned one fish. That's the goal here.
Okay. I guess we have another people asking, but I think it's you more or less answered. Will you touch the math behind RNNs and time series?
Yeah, so that would be a bit more advanced if there is enough interest, if we have fun in these three sessions, and if we want more, we can talk about um, another maybe three sessions to cover more advanced stuff. And there are things beyond that as well. There is the Hamiltonian Monte Carlo that is used in the search and exploration of the parameter space. There is the variational and Bayesian aspects of what we do in deep learning, but those are advanced topics. And if there is enough, let's see how this will go, and then we will talk about the more advanced topics after that.
Yes, and then okay, Alice is asked like, will there be a more advanced workshop, which you just answered. Definitely, like we always, I guess a broad answer is you ask for these features, and actually a lot of these features, a lot of these topics are very popular topic, and a lot of other people have asked. So we will see how this workshop goes, and see if we can have more advanced topics in the future.
Yes. So in the vocabulary of startups, let's do the lean startup approach. Let's do something, see what happens to that, and then decide where to go from there.
Okay, nice. I can't put that any better. Okay. So just a reminder, we do have a discount code. Now, the code I just posted on the chat, which is YT_launch30. So it's valid till 1 o'clock tomorrow. So it's valid basically within the next 24 hours, and then you will get $30 discount if you purchase a ticket today. So I think we're running out of time. So thank you very much, and thanks a lot, Amir, for joining us. And
Thank you.
yes, absolutely. If you have any questions or and about workshop or any questions in general, please feel free to ask us. You can email us if you are an ACE member. You can always Slack us on the channel. Okay, thank you very much for joining again, and I'll see you until next time.
Yeah, thank you, and thank you everyone. See you soon. Goodbye.
Bye bye.